Okay, thank you. It's great to be back in Tel Aviv, and I'm conscious that you're very hungry, and you're probably not hungry for what I'm about to talk about. But we do need to talk about the backlash that's starting to develop against technology. It's not just starting, it's actually been developing for quite a long time. I've been giving versions of this talk for over a year and a half. I started tracking this a couple years ago. You see this in the press. These are actually old quotes. Today's quotes are actually much more worrisome. There's been a number of books, but essentially the public is increasingly getting concerned about the technology that we're unleashing on them. Now, there's really two types of issues here. One of the issues that the previous two speakers focused most of their remarks on, which is that we as technologists haven't really engaged in the discussion with society about how the technology is going to be used, when it's appropriate to use it. For example, if it's facial recognition technology, when should you use it, when shouldn't you, and how it fits with the values of society. So that's one important discussion. Turns out that's actually the easier discussion to get engineers and technologists and programmers interested in. There's another problem that society has not yet become aware of. And when they become aware of it, they're going to be really angry with us. The second discussion is that in order to talk about how technology will be used and fit with social values, you need to know how the stuff works. And somewhere over the past couple years, I don't know how it happened, but it became okay to foist technology on people where we don't know how it works. So maybe we're transparent by making the code open source. But if you make the deep neural network open source and you don't know how it works and you haven't characterized it, we've stopped doing engineering. In fact, many university researchers even, the rot has spread all the way to the universities, aren't really doing what I call science or research anymore. So I'm going to go through some examples today. And this is, by the way, this is broader than AI and machine learning. I know this session is about AI and ML, but I'm going to start with some things that are not AI and ML. So you'll see this is a broader problem that's developed in some sense in the values that we've been using in the software world as developers and as technologists. Now, I'm an optimist, so I'm kind of delivering a bit of a pessimistic message, but for each area I'm going to say, oh, and there are things we can do. So I'm just angry that we're not doing the things that we should be doing. Okay, so one area, blockchain. By the way, I run a blockchain business, so I'm optimistic about blockchain. However, the Bitcoin blockchain, which we all became infatuated with, and many, many researchers at universities, et cetera, so it's researchers, VCs, everybody, the Bitcoin blockchain, let's think about it. It's primarily used, if you actually look at the real usage of it, other than speculation, it's primarily used for ransomware, right? How do you charge money for ransomware? So to facilitate ransomware attacks, to facilitate trade in kiddie porn, it's primarily used for bad things. Okay, we became infatuated with this technology. Why? Because it was based on a concept, proof of work. This is the Bitcoin blockchain. Sounds good, we all got really excited, but then if you really look at proof of work, it's really proof of energy wasted, right? Fundamentally immoral. I'm on the record on that one. By the way, the PR people at VMware weren't very happy when I started talking about things being immoral. Okay, but and on top of all this, the one thing that it promised was it will have decentralized trust, that it'll be decentralized. There'll be these thousands and tens of thousands of miners, so don't worry, one party can control it. And that's not true, right? If you look at pretty much all the public blockchains, they're controlled by very small numbers of groups of organizations. So those miners conspire and work together, et cetera. Okay, so that's the bad news. But I'm an optimist. We shouldn't throw the baby out with the Bitcoins. There's lots of good here. And in fact, if you can federate ledgers, if you weren't using this for cryptocurrencies and you think about federating ledgers and being able to have a shared sense of truth across organizations, this is really powerful. This can really change how we do business. It can change how audit works. It can change how regulation works, supply chains, financial technology. So great opportunities here. The really important thing going on is enabling decentralized trust. That's what we should be studying. There are efficient ways to do it using Byzantine fault tolerance, which is actually now where most of even the public Bitcoins are sort of backing into things that, if you look at them carefully, are variations of BFT. We've actually released an open source package based on the BFT that it's scalable, it's got low latency. So there's good reasons for optimism. But we really did not apply a lot of critical thinking to this for many years, and still many people are not applying critical thinking. If we look at some other areas, I'm just going to sort of skip this so we don't take too much time, but we can look at some other areas. Security, okay? This is, Cyber Week. But this is the situation that we as an industry have foisted on the customers. All right, if you want to run a large enterprise, you need to acquire at least 80 and probably 120 different products and figure out how to put them together yourself. And you still won't have really solved the problem, right? And you'll constantly have to add more. So who thinks this could possibly make sense? But actually, many of our best minds are contributing to this mess, right? Because if you go look, you'll find that most of the researchers, and you go to the conferences, the conference program committees, a lot of people should be taken out. In the US, we would say shot. Maybe here you would say spanked. But they should, the program committees keep accepting huge numbers of papers on exploits. Okay, so people find another exploit, and most of them are actually just based on new kinds of side channel attacks, et cetera, that we've known about since the 60s. So they're not really all that new. But this is essentially, it's become a business model for researchers. Because you essentially come up with a new exploit, you come up with a defense against the exploit, you go start the company, the VCs love it, and I used to be a VC, so the VCs love it. And then you sell the company on, and people have to buy the product because it fixes the exploit that you discovered, so it fixes the problem that you created. Okay, this is the business model. Very few people are actually working on how to systematically improve security. I mean, very few. I mean, I'm very frustrated. I go to the research conferences, and you find very few papers where people are actually trying to come up with ideas to systematically improve security. Okay, including here, I'm afraid. So there's a challenge for us. There's reason for optimism. We can do this if we try to do this, but we have to shift our thinking. Okay, privacy. I'm not going to talk about the concerns. Other people have spoken about privacy, so I'm only going to talk about the optimism, and it came up actually from our colleague at Intel. He mentioned 3 different techniques. There's at least one of the 3 he mentioned, differential privacy. This is really a glimmer of hope, and it's because a couple researchers, really led by Cynthia Dwork, starting about 15 years ago, stopped to say, well, we don't even have a definition of privacy. So they stopped and tried to, for at least some aspects of privacy, get a definition. And then, armed with a definition, surprise, surprise, they were able to reason about it. And now we actually have formal ways to reason about privacy, and people are figuring out how to turn those into tools. Companies like Google and Apple are actually embedding differential privacy in what they do. Now, this doesn't cover all forms of privacy. It's only good for certain types of issues and challenges. And again, our colleague at Intel showed other techniques that are available. So there's actually some hope here. We just have to have the will to make these things available and focus on them. And these are, again, issues about have we been really acting as scientists? So that's a case where people did, and it's getting, some adoption. Okay. So you sort of knew I was, at this session today, I'm going to talk mostly about AI and machine learning. Again, there's a lot of anxiety. Now, some of that anxiety is about the computers are going to take away all the jobs. We know from past history that actually when we have innovation, over time, the innovation initially does lead to some loss of jobs. And then over time, it actually makes something that's desirable very affordable. That leads to abundance. and then that creates a lot more jobs than were lost in the first place. So we know from sort of past cycles that there's a high probability that this will actually end up creating more jobs, not fewer. But the really important message is this time, people always, when they see these curves, say, but maybe this time it's different. Maybe this time the jobs won't come back. So I'm going to tell you it's actually this time it's going to be different. The really important difference, though, is the demographics. The important difference is that pretty much all the developed economies are facing a shortage of workers in the future. And in fact, even if you look at the less developed economies, so for example, you look at China, which is only developed in certain regions and not in others, they have a huge demographic problem. They're going to have a huge shortage of workers. They'll be the first country to get old before it gets wealthy. And even if you look at other areas like India, Southeast Asia, they're already seeing the curve starting to turn. So if we just say, well, let's not, AI, we're going to lose jobs, maybe this time it'll be different and the jobs won't come back. The reality is societies don't really have a choice. We need these new technologies in order to keep the lights on. If we want to keep having industrialized economies, we need to figure out how to adopt these. However, if we're going to do that, I'm going back to the technical issues, we as technologists need to face up to our responsibilities, and we haven't been doing this. And there's a couple different areas that we've just been ignoring. Or even worse, we've gotten infatuated with things and not paying attention to our responsibilities. So one aspect is there's a concern out there that the AI and machine learning will actually only be available to a few very, very large companies. And they'll be the only ones that can use it. So there's clearly an important challenge is to figure out how to democratize these technologies and make it so that other companies, not just the 6 largest companies in the world, 3 based in the US, 3 based in China, are the only ones that are really able to use this technology. Now, in order to do that, one thing is to take a look at the machine learning algorithms and to realize that some of the algorithms that those 6 largest companies are using, these deep neural networks, everybody's gotten infatuated with them. Everybody's trying to use them. They really only work really well. They're only superior when you have vast amounts of data, right? So Google, Facebook, they have vast amounts of data. Most other companies, the 99, I say the 99%, that's the Bernie Sanders line, but really if you look, about 99.9% of the companies, the enterprises, and we, at VMware, they're all our customers, they don't have those vast amounts of data. And in fact, they'd be just as well off if they used an algorithm that's well understood than if they used deep neural networks. But what do we give everybody? We give them deep neural networks because we're infatuated with them, even though we don't understand how they work. That's not being responsible. The other thing is we focus on the machine learning algorithms because that's the cool new stuff. But actually, if you go to deploy a machine learning system, click, okay, the click worked, you find that you need all this other stuff to deploy a machine learning system. And I'm not making this up. This is from a paper that the Google folks published. So this is a diagram we adapted from their work. So this gives you a sense of all the things. So we actually need, in order to democratize machine learning, need to figure out how to help people. The magic is actually not the machine learning algorithms. What Google and Facebook and Microsoft and others do really well is put the whole large system together, and we need to think about how to democratize that. So we've actually been funding university researchers to work on that challenge. This is one project at Stanford called Dawn, and I'm just going to play a little video clip about it.
Machine learning applications are developed by large, expensive teams of very well-trained individuals. And as a result, because it's so expensive to construct these applications, we find that ML is only applied in a small fraction of the domains in which it could be deployed and developed. The goal of Dawn is to make machine learning application development easier and cheaper, and therefore more accessible to a wide variety of users. We have large amounts of data, we want to extract value from this, but because we lack reusable systems and tools for automating some of the most tedious and expensive parts of the machine learning application development, essentially we see ML deployed in a much smaller set of domains we think could be possible.
So we can make this much more available so that it's not just used by 6 large companies. We need to be committed to doing it. Okay, but what we really need to talk about is not just how to democratize the technology, but these issues related to explainability and bias. Some of the speakers spoke about, and again, I'm not talking about the societal value part of it, although I'm very interested in that discussion. So it's an important discussion, we should have it. But what I'm concerned about is in order to have that discussion, we need to characterize, people need to know how the technology works. So as we start looking at this technology, and this is a diagram from one of my colleagues at DARPA, you need to be able to answer questions. So when the black box does something, the users want to understand, why did it do it? Why did something work? When does something fail? So we sort of have it fully characterized. So that's just the overall sense of explainability. If you don't have explainability, then as other speakers have indicated, you're subject to adversarial attack. Somebody earlier this morning actually said something like, oh, well, photos, if you're dealing with that, it can't be hacked. Well, of course it can be hacked. People are hacking photos every day, and this is going on. So this is just one of, you've seen earlier examples. You take a picture, you add a little bit of clever noise to it. It looks like noise, so the picture doesn't look like it changed. But the recognition software thinks it's something completely different. And that seems innocent enough. A less innocent example, you take a stop sign, somebody puts a few stickers, it looks like some children put some stickers on the stop sign. Now it's not a stop sign. Here's another example. The left-hand side, you have a car's driving, and if you look at the upper left, there's a lamppost on the street, there's a little shadow from the lamppost. The car, the shadow from the lamppost doesn't bother it. This is really good machine vision. It goes around the curve just fine. But now the adversary comes along and they paint another little line. So there's two shadows coming off this lamppost. Okay, this is what happens, right? So these things can easily be hacked. And if you don't understand them, you don't characterize them, this sort of stuff's going to be everyday occurrence. As the earlier speaker said, these systems easily can be biased either because of the training data or the algorithms. And we're starting to use these in so many important places in the justice system, in terms of credit checks, in terms of medical care. So again, if it's cat photos, then maybe it's okay. But when you start talking about serious use, it's not okay. And what really concerns me is there are things that we can do, right? So first, we should be working and learning how to explain, okay, deep neural networks, we don't understand them. I am amazed at the number of serious researchers that say, don't worry, let's just focus on how to use them. Researchers should, that should be like one of the most compelling problems for people to be working on today, is to understand why they work, when they don't. But it's going to take its time. That's a longer term problem. In the meantime, people will say, somebody quoted Musk, but many people will say, yes, but if it can save lives today, whether it's the autopilot example or it's, let's say, a system that can better diagnose cancer than the physician can, if it can save lives today, we should use it even if we don't understand it. But the reality is we should use it, but we should constrain it. We should think about how do we take the black box and surround it either with mechanisms that watch the inputs and the outputs. So that's one really good idea. This is from Emmanuel Candes at Stanford, which he's basically saying, it's hard to see here, I think there's the black box is the machine learning, and he's saying, okay, you don't really know how that works, but I can surround that with a layer of statistics where I can really reason and give you statistical guarantees on what goes in and what goes out of the box, right? If you tell me the statistics of what goes in, I'll give you guarantees of what goes out. I'll do things like I'll suppress false positives statistically, and now you'll be able to reason about the output. I think this is a really good direction. He's got a few examples of things he's tried, and this is like the sort of stuff I've been looking for, so I'm really thrilled to see it. Another thing you can do is create mechanisms to reason about the deep neural network. Maybe you don't let people use a fully general deep neural network, you let them only use certain types. And you say, well, can I then, for certain types, actually use formal methods to be able to prove that if you only change the input a little bit, the output will only change a little bit. You won't get dramatic shifts. You can't do that for generalized neural networks yet, maybe someday. But we can for a subtype of neural networks called binarized neural networks. The binaries, they're more binary in their decisions at the neurons, at the individual nodes of the network. And because they are, we can then convert the neural network into something that basically can be a SAT problem. And we're really good at SAT solvers, right? We know how to do that. So this is something that I'm really pleased about. One of our researchers at VMware, Nina Naroditska, and colleagues elsewhere, Amazon, people around the world, have been working on this, including also some researchers at Stanford. So there are things we can do, but it's just concerning that we haven't really been trying to do them, as a community. They haven't really been priorities. And doing these sorts of things to understand how the AI that we're foisting on the world works and characterize it has to be a priority. And backing up now to the more general, sort of theme that we've gotten okay with, foisting things in the world without understanding them. It worries me, and if I think about it, real engineers and real scientists and real researchers, they should at least be starting with definitions, right? And there's a surprising lack of definitions around many things we do. So, the privacy work, again, that's wonderful. Started 15 years ago. It's now bearing fruit, getting some definitions. Omer Reingold's doing some really nice work on fairness now at Stanford. And then on our own team at VMware, they work with Omer, but also have now started to actually put a definition around anomaly. Now, anomaly, I was going to bring this back to cyber. Anomaly detection is really important to cybersecurity. And we were stunned to find out that nobody actually had a definition of an anomaly. Let me tell you how an anomaly got defined in most research papers. First, they came up with their algorithm for anomaly detection, and then they worked backwards to tell you what an anomaly was. An anomaly is whatever my algorithm finds. If my algorithm works well on it, that's how I define an anomaly. Right? That's not very scientific. I don't know where the referees were on these papers, but this has been going on for a long time. So they stopped and really thought about what it means, and they've proposed a definition for an anomaly. And this may not be the best definition. Hopefully other researchers, it's how it's supposed to work, as other people will come and improve on it. So from a layman's point of view, what they're saying basically is it's an anomaly if really you can distinguish between two things, so you can distinguish a point, call it out, with only, a very small number of constraints. Like maybe just one constraint defines it. Because if you use many constraints, you're basically over-specifying. Then, any point can be called an anomaly if I can have an unlimited number of constraints. So the simple example here is, if you've got all these elephant pictures, you can, if you set the one constraint, look for the white one, right? So it can be, in that case, called out in one constraint. Now, from a more formal perspective, what they've really done is said, okay, if we have a multi-dimensional space and we map these objects into multi-dimensional space based on their properties, notice beauty of this is it's independent of the type of property. You can have many different types of properties. You map it into multi-dimensional space, you divide the space up into subcubes, and you look at the density of points in these subcubes, and the points that basically aren't very dense, those are telling you those are anomalous and interesting points. So they've done some work on that, and not surprisingly also come up with an algorithm that is efficient for finding those sorts of points. So we can do this. We can come up with definitions. We can come up with characterizations of how our stuff works. And I'm optimistic that this can be done. However, at the same time, I'm concerned that we've been teaching people as researchers. So it's not just like the Googles and the Facebooks of the world. It goes all the way, backwards up into the system, that it's okay to foist things on the world without understanding how they work. And we really need to change this. As technologists, as researchers, as engineers, we get to do these really amazing things that change people's lives and society. We shouldn't expect society to thank us for doing this. It's amazing we get paid to do this stuff because we get the satisfaction of really solving all these great problems. And it's really wonderful that society actually pays us to do it and allows us to do this. But we have a responsibility to know how the stuff works. And if the public ever finds out how much we've, allowed this to get out of hand, they're going to be really angry, and they should. So we need to get ahead of this, and we need to get back to doing really good research, science, and engineering. So I live in the San Francisco area. Just to close, this is one of my kind of favorite views and favorite places. It's, natural beauty. It's very nice. The problem is that if you live on the other side of the water there, it would be very inconvenient to get to this side of the water. So many years ago, people came up with a solution. They built this, the Golden Gate Bridge. It's elegant, it's harmonious, it fits in with its surroundings, and we know how it works. We understand it, right? We characterize it. So we need to do more stuff like that. Thank you very much.